You walk into a dark room, flip a switch, and the light comes on. To our human eyes, it happens in a literal instant. We naturally think of wires like empty pipes and electricity like water rushing through them. In this mental model, when you apply voltage at one end, the electrical pressure changes simultaneously everywhere along the path. But the laws of physics dictate that absolutely nothing travels faster than the speed of light. There is always a delay between the switch flipping and the bulb glowing. It's just that over the distance of a living room wall, that delay is measured in billionths of a second. Treating a circuit like a simple pipe that fills up instantly works perfectly well for a desk lamp. But when we scale down to the extreme speeds and tiny components of modern computing, that assumption completely falls apart. Inside a computer processor, data isn't a continuous stream of power. It's a series of distinct nanosecond-long pulses representing ones and zeros. At these extreme frequencies, the physical length of the circuit becomes comparable to the actual wavelength of the signal. The simple wire becomes what engineers call a transmission line, a structure with specific geometry built to guide high-frequency waves. A digital pulse in a transmission line isn't an immediate change in voltage. It is a physical wave of electromagnetic energy, and it takes a finite amount of time to travel from one end of the copper to the other. Eventually, the wave reaches the end of the wire. At these speeds, what happens at that final millimeter of copper determines if the data survives the journey or disappears entirely. That traveling wave of data eventually reaches its destination, usually a microchip or a receiving component waiting to read the signal. Every transmission line has a property called characteristic impedance. It's a natural, geometric resistance to the flow of the wave, dictated entirely by the physical shape and materials of the cable itself. This schematic illustrates a transmission line with its characteristic impedance, labeled Z0, hitting a destination load, labeled ZL. When the resistance of the destination component doesn't match the line's impedance, the boundary acts like a rigid wall. The destination cannot absorb all the incoming energy. The law of conservation of energy tells us that this leftover power cannot just disappear. The unabsorbed portion has nowhere to go but backward. Engineers calculate the exact ratio of the energy that goes in versus the energy that bounces back, a mathematical metric known as the reflection coefficient. At high speeds, a mismatched wire acts like a mirror, reflecting signals back toward the source. A single echoed signal is an engineering headache. But modern processors are sending billions of these digital pulses down the line every single second. The returning echo now travels backward, directly colliding with the very next incoming data pulse. When these physical waves collide, their voltages literally add together or cancel each other out right where they overlap. These graphs demonstrate what this collision does to the data. Look at the solid and dashed lines curving over time. The time delay and the returning reflection blur the sharp voltage step we expect, making it impossible for the processor to accurately read the signal. If the receiving chip can't distinguish a 1 from a 0, the communication link fails. This leads directly to system crashes, completely corrupted files, and digital chaos. To prevent this echo, electrical engineers use a solution called impedance matching. They artificially tune the internal resistance of the receiving destination so that it is mathematically identical to the characteristic impedance of the wire feeding into it. This creates a physical illusion for the incoming wave. Because the resistance never changes at the boundary, the wave behaves as if the wire simply extends onward infinitely. Under these matched conditions, 100% of the wave's energy smoothly enters the destination and is cleanly absorbed. This creates a state of maximum power transfer. It entirely silences the destructive echo, protecting the beta and restoring order to the circuit. This matching principle scales far beyond the microchips on a motherboard. The exact same physics apply to massive networks of fiber optics and transoceanic cables carrying light across the globe. Every modern router, server farm, and digital backbone relies absolutely on this precise tuning to function without collapsing under its own echoes. At this scale, the electricity powering our world behaves as a carefully guided physical wave, where the way we shape the end of the wire is just as important as the wire itself. Engineering these boundaries to perfectly absorb that energy allows our networks to sustain the speeds we've come to expect. It's the reason we can push billions of signals through a single cable every second, making the global internet possible.